Bismillahirrahmanirrahim. ELE424 Analog Electronics 1, welcome back. We are now at Video Pack 4 MOSFET. We have completed Video Pack 1, Semiconductor Materials, Video Pack 2, Diode Applications, and Video Pack 3, Bipolar Junction Transistors. So now we are on to our next main topic, which is MOSFET, and this is the first video on the Video Pack 4, which is on the MOSFET device. I am Wan Fazlidah Hanim Abdullah. I'm from the Faculty of Electrical Engineering, UiTM Shah Alam. Okay, the topics covered in MOSFET device set 1. First, as usual, we'll do the introduction, because once you see what the introduction is, hopefully you will see how this topic fits into the overall syllabus. And then we'll have a look at the MOSFET construction, MOSFET operation, and some non-ideal behavior and other types. For the introduction, we'll first look at the MOSFET and its impact, why this is in the syllabus in the first place, the MOSFET types, and the contents that we will cover for this session. So, MOSFET impact. The metal oxide semiconductor field effect transistor, so the MOSFET MOSFET, is a major type of transistor, just like the BJT is one of the major types of transistor, and in fact it is the major type of transistor in the sense that it led the electronics revolution of the 1970s and 1980s, in which the microprocessor made possible powerful and portable computers and all sorts of sophisticated electronic systems. MOSFETs make for more than 90% of the transistors in the world. So the MOSFET can be made very small because the construction is simpler than BJT. So high density, very large scale integration VLSI circuits, where you can have hundreds and thousands of transistors in one small chip, is possible, and high density memories are also possible. Digital circuits can be designed using only MOSFETs with essentially no resistors required, because MOSFETs, other than switching, it can also be designed to act as a resistor as well as a capacitor. So you can have a circuit without having to have an external component. Okay? So MOSFETs can also be used in analog circuits, and that's why we have MOSFETs in the syllabus of ELE424. So just going through the flow of diode and then BJT and then MOSFET, just so that you see what the overall flow is. Diodes have only two terminals with one PN junction. It is useful in rectifying circuits, clipper and clamper circuits, and voltage regulators. We know that. Then we moved on to 3 or more terminals transistors. So why do we have 3 terminals? Why can't we just have 2? Because when we have an extra terminal, a general concept is that when you have 3 terminals, you can have a small voltage and or current applied at one terminal controls a larger electric flow through its other 2 terminals. Okay, so that's what we have demonstrated in this diagram here. So ELE424 will cover 2 types of transistors, BJT, which we have done, and now we are going to look at metal oxide semiconductor field effect transistor. Just before we move on, diode allows current flow in one direction based on the biasing applied across its 2 terminals. So this is a symbol. Okay, you have VD and ID, but transistors offer a control terminal that decides the flow between the 2 other terminals. So BJT, you had this, if it is a common emitter mode, then you have an input current at IB and VBE, and then you have VCE and IC. But in this case, in the MOSFET, for example, you have VGS controlling ID. Okay, so now let's have a look at the syllabus contents. So there are 2 complementary devices under MOSFET, which we will call the N-channel MOSFET, we will call NMOS, and the P-channel MOSFET, PMOS. Okay. In this session, we will study and understand the structure, operation, and characteristics of the various types of MOSFET, of NMOS and PMOS, enough for us to proceed to DC analysis and design techniques of MOSFET circuits for ELE424, and the courses that follows after this. And the IV characteristics of these devices are introduced, that's what we're going to do, and the DC analysis and design techniques of MOSFET circuits are developed. After that, we will cover small signal AC analysis. So from this topic, we will be going on to semiconductor devices later on, if you're in the program EE241, okay, or any other programs, and then there's going to be ELE426, that's going to be direct, which is Analog Electronics 2, or you can also be looking at these circuits when you do integrated circuit design. Okay, another type of field effect transistor is the junction FET, JFET. Okay, two main types of JFET are PN junction FET and the metal semiconductor field effect transistor, which is MESFET. But these are not covered in the syllabus of ELE424. JFET was discovered before MOSFET, but in this case, MOSFET's use has surpassed JFET. There may be some applications that may still want to use, but it is not as dominant as MOSFET. So it's not covered in ELE424, only MOSFET is covered in ELE424. We have completed introduction. Now let's have a look at the MOSFET construction. We will first look at what the symbol is, because when we design circuits, it's always handy to represent the MOSFET in its symbol form. And then we'll have a look at a simplified version of what the MOSFET actually looks like through its cross-section. And then we'll focus on the heart of the MOSFET, where the action is, the main action takes place, which is the MOS capacitor. And then we'll have a look at what an NMOS enhancement device looks like and how it operates, and then the PMOS enhancement device, and just a very quick look at other types of MOSFET types. Okay, so I'm picking this up from the introduction part. We said just now that there are two complementary devices, the N-channel MOSFET, NMOS, which we'll call NMOS, and the P-channel MOSFET, which we will call PMOS. Now, in the text, when it says NMOS and PMOS, it's usually referring to the enhancement mode device, which you will see later on what it means. Okay. For each, there is a slightly different symbol and biasing configuration. There is also a slight difference in the current voltage characteristics. It's slightly, but it is significant to operation because of the doping type. It's just like, you have NPN and PNP, but in this case you have NMOS and PMOS. The device construction is also different in terms of dopant type. So these are the symbols that we are looking at. The part A here refers to a symbol that we would see in simulators or maybe in some other text. But this textbook that I use as the main reference for MOSFET, which is microelectronic circuit analysis from Neamen, is it will be using this symbol where it shows 3 terminals only, but not the fourth, which is the bulk, which I will explain shortly. So 4 terminals, there are 4 terminals: drain, gate, source, and bulk. Okay, VGS, which is the voltage between the gate and source terminals, controls the channel formation. VDS, which is the voltage from the drain to the source terminal, compared to VGS minus VTN, you'll see later what all this means, determines the region of operation. VSB, okay, B is the bulk, ensures the current does not flow from drain or source to body. Now usually the bulk is either tied to source or it is connected to ground for reasons to make sure that the regions between the source and drain and the substrate are reverse biased, so that the current does not flow from drain or source to the body. So usually we know that the fourth terminal exists, but it's not explicitly shown. Okay, so in this text we'll be using this terminal, and it's also easy to draw. This is the PMOS terminal. PMOS symbol. Okay, so again, this is the symbol that we'll see in simulators. It's the same as NMOS. Okay, for the text, it will use a symbol, but it will just use drain, gate, and source. There are 4 terminals: drain, gate, source, and bulk. But if you see this PMOS, we would usually indicate source at the top and drain at the bottom. Okay, when it was NMOS, it was drain at the top and source at the bottom. So in this case, it's the other way around, because it simply means that we will be biasing the source higher than we will be biasing the drain. And the voltages that we refer to, in NMOS it was VGS, but in PMOS it would be VSG. Okay, VSG, and instead of VDS it would be VSD. So VSG controls the channel formation, and VSD compared to VSG plus VTP determines the region of operation. Here it's plus because we are not putting a modulus at VTP here. Okay, and usually the threshold voltage for VTP is usually negative in the models, device models. So anyway, VBS, the bulk here would usually be tied either to the source or to the highest point, the highest terminal, the highest biasing of in the circuit, to make sure that the regions between the source and drain is reverse biased with the body, so that the current does not flow from drain or source to body. So we just assume, because it's the same across all transistors, we assume that it's been taken care of, and we will only consider these 3 terminals. Okay, but there will be in other courses that you will see where you might have to consider the 4th terminal, like what you do in IC design. Alright, so cross-section of NMOS. This is the cross-section of how it actually looks like. Okay, a simplified version of what it would look like if you take a picture under a scanning electron microscope of the device, of how it would look like. So it would have source, okay, gate and drain, source, gate and drain, and the substrate here, which is the semiconductor body. Okay, the source is actually is in contact, is the contact point for this region here, this heavily doped region here, and it is the same as the drain. Okay, so you have the gate oxide, the gate, okay, the gate, which is usually polysilicon. Okay, the metal is actually replaced with polysilicon. Okay, this is the polysilicon, and then there is an oxide here and a p-type substrate regions, and this is what forms what they call as a MOS capacitor. It's actually just like a parallel plate capacitor where you have conductor sandwich in between is the insulator. Okay, so here you have a metal oxide semiconductor. So there are 2 N regions called the source terminal and the drain terminal here. Okay, source region and the N region. So the terminals are the metal contacts to this heavily doped regions here. Okay, so if you look at a MOSFET structure like this and you see that the source and drain are N+, then it is an NMOS. Okay, and the current in NMOS is the result of the flow of electrons as between source and drain in the inversion layer or the channel region. Okay, we'll have a look at that statement in more detail in the slides after this. We're still looking at how the MOSFET looks like. Okay, so L is the distance between source and drain. Okay, distance between source and drain, and W is the width of the gate. Okay, now we're looking at PMOS. You still have the gate, the oxide, but now you have the N substrate, not the P substrate, and these are what forms the MOS capacitor region, just like I said just now, like the parallel plate capacitor where you have metal and semiconductor N-type acting like the conductor, and the insulator in between the parallel plates, in this case, is the oxide. There are 2 regions called the same thing, called the source and the drain, and you have the terminals to have to apply bias. These are the metal contacts to the source and drain regions. And for PMOS, this is P-type. Okay, the source is P-type and the drain is P-type. So if you look at a MOSFET structure and you see this P plus here at the source and drain, you know it is PMOS. Just as if you look at this structure and you see N plus and N plus here, it is NMOS. So the N plus is just to say that it is heavily doped. Okay, the concentration is high. The current in PMOS is the result of the flow of holes between source and drain in the inversion layer or the channel region. And if you look at, I'm gonna go back to NMOS. If you apply voltage at the gate, it means that you're applying VG, and you apply voltage at the drain, you're applying VD. But in a lot of the expressions for MOSFET, it's actually what you're considering is VGS, which is the voltage from the gate to the source, and VDS, which is the voltage from drain to the source. Same thing as PMOS. You have you can apply VS, VG, and VD, but VSG is what is put into the expressions. So you have voltage between the source and the gate, and VSD, which is the voltage between the source and the drain. And L again is the same thing, is the distance between source and drain, and W is the width of G. Alright, before we carry on, the yellow slide. Okay, the yellow slide is just a revision which can go back either from your foundation years or secondary school. So let's have a look at parallel plate capacitance. A parallel plate capacitor shows a top plate. Okay, you have parallel plate, in between is an insulator. Shows a top plate at a negative voltage with respect to the bottom plate. An insulator material separates the two plates. Okay, so this is an insulator material. This is just any parallel plate capacitance that you studied before this. So with this bias, if you apply negative voltage at the top and positive voltage at the bottom with this DC source, voltage source, okay, a positive charge would exist at the on the bottom plate, and an electric field is induced between the two plates as shown. So you have here a collection of positive charge, because this electric field makes the positive charge to want to be attracted to move in the direction of the electric field. So the capacitive action, you have this capacitive action produces a collection of positive charge at the bottom plate and a collection of negative charge at the top plate, causing this electric field to be induced. Now this capacitive action is affected by the permittivity and the area of the parallel plates and the distance between them. So permittivity is determined by the insulating material characteristics. Now using that concept, the heart of the MOSFET, as I mentioned earlier, is the metal oxide semiconductor capacitor, or we call it MOS capacitor. Okay, so this is what you have. In most cases, the metal is replaced by high conductivity polycrystalline silicon layer deposited on silicon oxide. This is just extra information for you. The parameter Tox is the thickness of the oxide, and permittivity epsilon ox is the oxide permittivity. So this controls the capacitive behavior at this section. So what is it going to do actually? So the bias between the gate and source will determine the carrier's presence in this channel region under the gate between the source and drain. Now let's see what we mean by that. Now consider this configuration of biasing. Okay, in this case we connect the negative terminal of the voltage source to the gate and the positive terminal to the bulb. So with this VG as shown, electric field causes accumulation of holes. Okay. Electric holes are attracted to this direction because this is going to be positive, and the electric field will be in that direction. But if we have the voltage supply connected in this configuration, so which means that you'll be accumulating the positive charge at the top plate, but at the bottom plate what you're going to do is that, okay, it causes the positive carriers, which is the holes, to move away from this channel region. So with VGS causing E field in the direction, but it is less than threshold voltage, we will see what it means later. It causes a depletion of holes even though the substrate is p-type. So in depletion case here, you have induced a negative space charge region here. There are no more holes here. The holes have all been driven away. But if you keep on increasing the biasing of this voltage source, okay, up to a value that is equal or greater than the threshold voltage, with VGS causing E field in the direction shown, but is equal or more than the threshold voltage, not only that it drives away the holes, it induces an electron invasion layer here. Okay, so now this is a p-type substrate, but this region here, okay, has become an electron inversion layer, not by doping, but by biasing, but by the capacitive action of the MOS capacitor. So now this region below here has been inverted to have abundance of electrons, and this channel region is now inverted to have an abundance of electrons, even though it is p-type substrate. This is what I've just stated just now. So with PMOS, it's the same thing. If you have the voltage source in this configuration, what you have with the N-type, because with PMOS, the source and drain regions are P-type, but the substrate is N-type. So if you do it this way, you can have a accumulation of electrons in the N-type substrate. But if you apply VSG in this direction, okay, what you do is that you drive away the electrons in the substrate, causing this induced positive space charge region, just as in MOS, but it's in the opposite opposite type polarity. Okay, so now here with VSG causing electric field in the direction shown but is equal or more than the threshold voltage, it induces hole inversion layer. So even though this is N-type, we have now inverted this channel region into holes with abundance of holes, even though it is an N-type substrate. So this channel region between source and drain, what's the big deal? So this phenomenon used to modulate the conductance of a semiconductor with an electric field perpendicular to the surface and perpendicular to the direction of the current is called the field effect. Okay, hence the field effect transistor. So the formation of the inversion layer, the whole deal is it allows current to flow between source and drain. So if you have here, this is just a quick scribble here. So I have here source and drain. If it is NMOS, so if there is no inversion layer here between the source and drain, there will be no area that the electrons can flow. But if you have an inversion layer, the electrons can now flow, okay, if you apply drain source voltage. So the gate source voltage ensures that there is an inverted layer under the channel region, at the channel region, and the drain source layer will cause the carriers to flow by applying the right electric field between the source and drain. So VGS forms the inversion layer, okay, so that there are carriers there of the right type that can connect the source and drain. But VDS, which is the drain source voltage, allows the carrier in the channel region to flow between source and drain by applying the correct electric field in the direction between the source and drain. So VDS with respect to VGS affects the current flow and region of operation of the carriers that are already in the channel region. ID is determined by VGS and VDS. So now let's have a look at, again, before we leave, applied bias and currents in NMOS. So the threshold voltage of NMOS, denoted as VTN, is the gate voltage with respect to source voltage required to turn on the transistor. Okay, if VGS is less than VTN, ID is essentially 0. Okay, if VGS here is less than threshold voltage, ID is essentially 0, and if VGS is greater than VTN, ID flows if VDS is applied. So VDS needs to be applied to make sure that this carrier flow. Otherwise, if the carrier is just there, it simply means that the channel region has been inverted. The carriers are there, but it's not flowing yet. Okay. But then if you apply VDS without applying the gate source voltage to invert this layer, even though there is an electric field, but you cannot cause the carriers to flow because the carriers are not there. So VGS forms the channel, VDS causes the carriers in the channel to flow. So electron flow from the source to drain with an applied VDS, and what it's saying here is that it flows. So if this is an N channel, NMOS, okay, it flows from source to drain, but then the conventional current is in the opposite direction of electron flow. So the conventional current enters the drain and leaves the source. Okay, so since gate is separated from the channel by an oxide or insulator, so this is gate, this is the channel, this is an insulator, and insulators is not supposed to conduct current, so there is no gate current. There is no current except for a very small leakage current, which we can safely say equals to 0. So there will be no IG. Okay, this terminal does not draw current. The current is only between drain and source. So similarly, since the channel and substrate are separated by a space charge region, this one is separated by a space charge region. What is the space charge? Depletion region. Okay, and because we said just now that the bias of the body must ensure that the PN junction between the source and the body and the drain and the body are reverse biased, so that there is no current going from the source or drain to the body, because we want the current that is formed, the carriers that are formed in the inversion layer, whatever current that you apply from VDS, it has to flow from source to drain, not from source to body or drain to body. Okay, now the same thing with PMOS. Threshold voltage PMOS is denoted by VTP. It is required to turn on the transistor. If VSG is less than VTP, ID is essentially 0. If VSG is greater than VTP, ID flows if VSD is applied. Okay. Holes flow from source to drain with an applied VSD. Okay. So the conventional current enters the source and leaves the drain. Okay, because conventional current is in the direction of positive current flow, positive charge flow, which is holes. And the same thing, since gate is separated from the channel by an oxide, there is no gate current, so IG is 0. Similarly, since the channel and the substrate are separated by a depletion region or space charge region, there is essentially no current to the substrate. Okay, this space charge region here refers to depletion region. It's the same thing. Neamen uses the term space charge region. Now we are ready to look at MOSFET operation. We'll have a quick look at what basic concept is and the equations that are related to NMOS and then to PMOS. Okay, so I have purposely just drawn a hand-written the symbol, okay, between drain, gate and source, gate and drain. Okay, so the basic transistor principle is the voltage between two terminals that controls the current through the third terminal. So we control VGS to control ID, okay, or VSG to control ID. Question is, will it conduct? And the question is, in what region of operation will it conduct? So let's first have a look at the transfer characteristics. What is the transfer characteristics? If a fixed value of VDS is applied, okay, meaning that you have already applied VDS. So if there are carriers in the channel, it can flow. If there are no carriers in the channel, it cannot flow. Okay, and VGS, the gate source voltage, which is the voltage across the MOS capacitor, is swept from a value much less than threshold voltage VTN to the value VTN and to a value greater than VTN. MOSFET transfer characteristics ID versus VGS is as shown. If it's less than VTN here, there are no carriers that is of the same type of the source and drain. Okay, so meaning that there will be no current here. But once you reach threshold voltage, okay, there'll be an inverted layer. That inversion layer will cause, because there is a VDS, the current will flow. So there will be a value for the drain current ID. Now let's have a look at the output characteristics. The transfer characteristics is ID versus VGS, but the output characteristics is ID versus VDS. Now once VGS is greater than VTN, meaning that the channel region has the inversion layer, NMOS can conduct current if VDS is applied. And depending on the value of VDS, NMOS will operate either in triode region, or we call it non-saturation region, or the saturation region. Okay, now this region here, some people call it linear region, some people call it triode region. Okay, but this is at this region here, you will see that ID increases, well, almost linearly. That's why they call it linear region. But here, after the triode region, it becomes horizontal, so it saturates. So that's why it's called the saturation region. So the value of VDS that separates the triode from the saturation region, sorry, there's a typo there, is VDS set, where VDS set is equals to VGS minus VTN. So if you can just imagine, VTN is a value from the device model parameter, meaning that it's not a value that that is applied as such. What you apply is VGS. This VTN here is a value that represents the MOSFET. Okay, it is defined by the people who fabricated the device, and it is usually a given value. Okay, so, or it may change slightly, but there is a base value, a reference value for the threshold voltage. So VDS here, once you apply VGS greater than VTN, meaning that there is an inversion layer, but VDS, if it is greater than VDS set, it will saturate. That's what it's saying. If you apply VDS less than VDS set, it will be operating in the triode region. So the expression of ID, because you're going to have an equation, an expression that says what ID is with respect to VGS and VDS. Okay, it depends where the region of operation lies, whether it's in triode or whether it is in saturation region. So now let's have a look at what the expressions are. So if it is in triode region, where VDS is less than VDS set, okay, so this line here is VDS is equals to VDS set, which is equals to VGS minus VTN. Okay, these are all values. Okay, so when you look at the biasing of the MOSFET, you can decide whether it's in triode or whether in saturation. So if it is in the triode region, the formula for ID is Kn times this big bracket here, which is 2 times VGS minus VTN times VDS minus VDS squared. Okay, the values that you bias the transistor with is VGS and VDS. Okay, gate source voltage and drain source voltage. VTN is a value that is given for the particular MOSFET. Kn is the transconductance parameter, which is equals to mu n C ox W/L, which I will show later. But okay, now if it is in saturation region here, where VDS is greater than VDS set, meaning VDS is greater or equal to VGS minus VTN, the expression for drain current is ID equals to Kn VGS minus VTN squared. Okay, so essentially what it's saying here is that in the triode region, it depends on VGS and VDS, but in the saturation region, it is mainly affected only by VGS. Okay, even though you increase VDS, the line remains horizontal in the saturation region. So the term Kn is the transconductance parameter, the term Kn here, which is equals to W over 2L times mu n C ox. Now mu n C ox, this mu n C ox here, is what you call a process conduction parameter because it comes from the fabrication process. The fabrication of the transistor itself, the kind of material it is, the kind of concentration of N-type and P-type concentration, and the type of oxide that it uses. These are all determined by the fabrication process. But W and L, okay, if you remember when we covered just a few slides ago, where we had L to be the distance between source and drain and W is the width of the gate. Now those are just the layout. Okay, it comes from the layout that forms the structure, and these are what you call the integrated circuit design parameters that determine the size of the transistor. Okay, so those W and L determines the sizing of the transistor, whereas mu n C ox comes from the fabrication. But whatever it is, this value Kn here is used whether it is in triode or whether it is in saturation. But if it is in triode, ID follows this equation above here, and if it is in saturation, it follows the equation below here. How do we know whether it's in triode or saturation? We look at VDS. If VDS is less than VGS minus VTN, it is in triode. If it is greater or equal to VGS minus VTN, it is in the saturation region. So example, consider NMOS with the following parameters. VTN equals to 0.4 volts and Kn equals to 1.4 milliamp per volt squared. Determine the current when the transistor is biased in the saturation region for VGS equals to 0.8 and VGS equals to 1.6. Okay, it says that it's in the saturation region, so we don't actually need VDS here because we are assuming an ideal device. Okay, and we have VGS, and therefore we use the equation Kn VGS minus VTN squared, not the formula above here because this would be in triode, so we choose this one because it's already stated that it is in saturation region, and we get the value of ID to be Kn, which is 1.4 times VGS minus VTN, which is 0.8 minus 0.4 squared, which is equals to 0.224 milliamp. And if VGS is 1.6 volts, ID is equals to 2.02 milliamp. What about if it's PMOS? If it's PMOS, it's the same concept except that all the VGS has changed to VSG and all the VDS, drain source voltage, has changed to VSD, which is source drain voltage. Okay, the values for VTP here, because we have not stated it as a modulus value, so it's minus negative becomes a positive value here, VTP. And the term Kn becomes transconductance parameter. And Kp is mu P Cox, which is the mobility of holes times Cox. Again, that's process conduction parameter. And W and L are it comes from layout that forms the structure. So this is a summary of the MOSFET current voltage characteristics. Okay, we have to check if we want to know which value or which expression of drain current we need to use. We'll have to check the value of VDS. Is it greater or equal, or is it less than VGS minus VTN? Okay, that's what you call the transition point, VDS set or the VSD set. Okay, this is an example. I'm not going to solve it here. An NMOS transistor with VTN equals to 1 volt has a drain current ID 0.8 milliamp when VGS is 3 and VDS is 4.5 volts. Calculate the drain current when VGS is equals to 2 and VDS equals to 4.5. So what's going on here? Okay, it doesn't give you what Kn is. So I assume that from this expression, you have threshold voltage, you have drain current, you have VGS, you have VDS. First, based on VGS 3 volts and VDS 4.5 volts and a VTN of 1 volt, you have to decide this combination of 0.8, 3 and 4.5, is that in saturation or is that in triode? Once you decide that, you can find the value of Kn. Once you find the value of Kn, you can now calculate the drain current. Okay, then it gives you another set of value, which is VGS equals to 2 and VDS equals to 4.5. Now you have to compare VDS. Does it exceed VDS set? And the same thing, how do you know what is VDS set? VDS set is equals to VGS 2 volts minus VTN, which is 1 volt. So 2 minus 1 is 1. And that makes it VDS set. But this is for VDS 4.5 volts, so maybe it's in saturation. Then you have to do the calculation based on using the value of Kn that you have found. Okay, try this, and we'll discuss it in our online discussion meet when we see each other. This is also the same thing, but this is a PMOS device. Okay, this gives you a threshold voltage VTP. It has a drain current. It gives a drain current with VSG and VSD. Again, it does not give you Kp, so you can find Kp from here. From the value of Kp, but before you find the value of Kp, you have to decide whether this combination of 3 volts of gate source gate voltage and 5 volts of source drain voltage with this VTP negative 1.2, is that going to be in saturation or is it going to be in triode? Okay, find the value of K. Once you know what the value of K is, then you can find the drain current. The answers are here. Again, we'll discuss this when we meet each other. Now, before we go off, we'll have a look at non-ideal current voltage characteristics and other MOSFET types. The text, okay, covers 5 non-ideal effects in the current voltage characteristics of MOS transistors. The finite output resistance in the saturation region, 1. The body effect, 2. Subthreshold conduction, 3. Breakdown effects, 4. And temperature effects. But at this stage of ELE424, I will only touch on finite output resistance in the saturation region. So finite output resistance on saturation region, because just now we said when it's ideal, once it saturates, it's a horizontal line. So it's the same thing as BJT here. Once it enters the saturation region, now it's not horizontal anymore, but there is a slope. So in the ideal case, when a MOSFET is biased in the saturation region, ID is independent of VDS. That was in the ideal case, meaning ID is horizontal in the horizontal saturation region. However, in an actual MOSFET, especially when the distance L becomes smaller and smaller with the scaling down of the fabrication technology, you will find that the saturation here becomes steeper and steeper. Okay, so in actual MOSFET ID versus VDS characteristics, there is a non-zero slope. Okay, a non-zero slope does exist beyond the saturation point, and the reason for this is channel length modulation. So I'm not going to cover what channel length modulation here is, but it is in the book. We'll discuss it on the online. Introducing lambda, okay, as channel length modulation parameter. So saturation ID, now the formula now, which was in the ideal behavior, was ID equals to Kn VGS minus VTN squared. Now it's VGS minus VTN squared times 1 plus lambda VDS. Now if you look at the equation for the drain current in the saturation region, okay, this is the saturation region and this is the extension that it's added. Now there is a term VDS, which means that it is affected by VDS, even though not as significantly as in the triode region, but it is affected by VDS. So we have factored that into our drain current equation in the saturation region. How do we find this slope value? Okay, so the slope is, if you use Ohm's law, okay, the slope is going to be the inverse of 1 over R out. Okay, so 1 over R out is going to be, if you do a partial differentiation of ID with respect to VDS, okay, and if you differentiate this expression, okay, and inverse it, this is what you're going to have. R out is equals to lambda Kn VGS minus VTN squared. Okay, VGS, which is the Q point that we are going to operate at, the point that we are interested in. Okay, so if you have the value of Kn, the value of VGS, the DC value of VGS that you are biasing it, and VTN with the value of channel length modulation parameter that is given for the device, you can straight away find R out. If you do not have all this, you can find it from the graph itself by finding the slope and getting the inverse of it to find R out. Okay, or if what is given, remember the early voltage in BJT. Okay, the early voltage is actually the inverse of the channel length modulation parameter. If you have just the value of the channel length modulation parameter or the early voltage, and you know what the Q point is for the current, then you can just find it from this expression, VA over IDQ, or equals to 1 over lambda IDQ. Now, other MOSFET type, which we do not focus in this course so much. One is the depletion mode. The term enhancement mode means that a voltage must be applied to the gate to create an inversion layer. But there is another type of MOSFET, okay, that is called the depletion mode MOSFET. Now, in depletion mode MOSFET, it is ready to conduct with the carriers in the channel region even without bias. It is always on. So negative gate source voltage needs to be applied to remove the inversion layer. So you need to apply negative voltage to turn the device off. So there may be occasions where you might need a depletion mode device, but in our syllabus here, because enhancement mode is the more widely used, we will focus on the enhancement mode device. So there is NMOS enhancement, PMOS enhancement. Okay, remember we've just done that in the subsection earlier. And then there is N-channel depletion and there is P-channel depletion. And now before we just go off, I'm just saying that when you do circuits, okay, whether it's in digital circuits or later on, usually you have a combination of PMOS and NMOS in the same circuit. Okay, it's not like the BJT. You don't have you do not see NPN and PNP together in a digital module circuit. Okay, but what you see here, CMOS is very common. Okay, so CMOS is complementary metal oxide semiconductor circuits, which is a combination of PMOS and NMOS. It simply says that in the circuit there is PMOS as well as NMOS. Okay, so that is CMOS. So if you will see a lot of semiconductor industry talking about their CMOS technology. It simply means that they are fabricating both PMOS and NMOS, and that is the circuit approach, the circuit design to go for the digital modules as well as the analog circuits. Okay, so next we've done MOSFET device. Next, we will cover MOSFET DC analysis. Now, there are many circuits that can be constructed using MOSFETs. Okay, either it's analog or digital, or even within analog itself too, there are many circuits that you can do. But what we are going to do for ELE424, the syllabus only covers small signal amplifiers, and that is what we're going to do in the next video of MOSFET DC analysis. Thank you very much. See you in the next video. Assalamualaikum.